Problem number 2. Consider two functions, f of x equals 2x and g of x equals sine x on the interval negative 2 pi to 2 pi. And again, we're going to graph f composed with g and g composed with f, and we're going to compare. What different role did multiplying by 2 play in the two functions? So again, my first task is to find f composed with g and g composed with f. So here's f composed with g, and that is synonymous with f of g of x. Another way of writing the same idea. And let's see, in f composed with g, that means I take g of x and plug it into f of x. So f of x starts with a 2, and then I get x. But instead of writing an x, I'm going to write g of x, which is sine x. So it's going to be 2 sine x. And this one, I'm going to keep the same interval. So this is going to be on negative 2 pi less than or equal to x less than or equal to 2 pi. And then for g composed with f, that's another way of writing g of f of x. I start with the graph of g, and when I get to an x, I plug in f of x. So the graph of g starts with sine, but then I see an x. So instead I write 2x. And it's going to be on the interval from negative 2 pi less than or equal to, oh, I see an x. I'm going to write a 2x less than or equal to 2 pi. And it's weird to have the 2x there in the domain restriction. So I'm going to say this is like sine of 2x. And I'm going to divide everything by 2 to get rid of that 2 and the 2x. So this is going to become negative pi less than or equal to x less than or equal to pi. So now I'm going to graph my first graph, which is f composed with g. And I'm going to do it in blue. This one's going to be blue. And I'm graphing a sine curve, but the amplitude is going to increase to 2. And it's going to be back at 0 at pi and back at 0 at 2 pi, because I know the interval is 2 pi on a sine curve. And same thing, graph 2 full intervals here. I know that at pi over 2, we're going to go up to positive 2. At 3 pi over 2, we're going to be down at negative 2. And let's see, halfway across, 1 there, 1 there. We're going to be down to 1 down there, right there. That looks pretty nice. And hey, that looks pretty good. Now the other side, negative 1, negative 2, negative 1, 0, 1, up to 2, 1, there we go. Okay, there's f composed with g. And then in red, I'm going to graph g composed with f. This is a dilation about the y-axis. All of the points are going to get compressed towards the y-axis, including the domain restriction we saw. So this is only going to go from negative pi to pi, but the whole entire period is shifted inwards. So we're still going to get 2 full intervals. So let's see. I'm going to be halfway across, I'll be at 0. And halfway across, I'll be at 0. And we're only going to have values that go up to positive 1, because we don't have that dilation vertically, and down to negative 1. Down to negative 1 and up to 1. So we get a graph that looks like not quite as pretty as my blue one, but that's okay. And that is, oh, I shouldn't have been doing those arrows, huh? That whole way through. Let me white that out. We were not doing the entire 2 pi. That should be a closed circle there and a closed circle there. We were only on that one interval. Close, get rid of that. Get rid of that. My bad. There we go, that's better. This is negative 2 pi, negative pi. Cool. Okay, so, and that was G composed with F. So by way of comparing the different role that the transformation times 2 played in the two functions, I wrote in F composed with G, the times 2 is multiplying the outputs of the sine function. Dilating the graph of g of x, which I drew here in purple, away from the x-axis. You can see all the points go away from the x-axis. The blue points are all further from the x-axis by a factor of 2. So they're all twice as far from the x-axis as they used to be. So 1 got twice as far, now it's 2. A half is twice as far away, now it's 1. Negative 1/2 is twice as far away, now it's negative 1. Negative 1 is twice as far away, now it's 1. In G composed with F, the times 2 is multiplying the inputs of the sine function, meaning that any given x value input in G composed with F will have the same output as an x value input of twice the magnitude in G of x. I think of G composed with F as a dilation of G of x by a factor of 1/2 about the y-axis. Your textbook refers to this transformation as a compression of the graph about the y-axis by a factor of 2. So your textbook uses the phrase compression versus stretch to indicate dilations that get bigger versus smaller. I just say dilation, and then it's a factor of more than 1 if it gets bigger, and a factor of less than 1 if it gets smaller. But otherwise fine. You'll notice that if we compare the purple graph of g of x to the red graph of G composed with F, here this point 2 pi was dilated towards the y-axis by a factor of 2, or 1/2, depending on how you think of it. So this point 2 pi became just pi. This point pi became pi over 2. This point pi over 2 became pi over 4. But this point just stayed where it was. Negative 2 pi became negative pi, etc. All the points are shrinking towards the y-axis. Again, remember that though I am dilating about the y-axis, this G composed with F transformation is a transformation of the x-coordinates. It's the x-coordinates that are dilating towards the y-axis. Whereas when I transform the y-coordinates in the first transformation, F composed with G, it was the y-coordinates that were dilating towards the x-axis. It would probably also be good to note that F composed with G did not impact the domain restriction, whereas G composed with F did impact the domain restriction. F composed with G was a transformation of the range. It had no impact on the domain, whereas since G composed with F was a transformation of the domain, it had no impact on the range. This domain restriction that used to be negative pi less than or equal to
x less than or equal to 2 pi became negative pi less than or equal to x less than or equal to pi. This transformation of the domain occurred by replacing x with 2x, which meant that then if I wanted to isolate x, I had to divide by 2, further illustrating the manner in which the transformation of the x values occurred in an inverse manner. Plugging in 2x made the values half as large. You'll see here that I have added in a Desmos calculator in this slide because I think this is a transformation that is well worth illustrating dynamically. So let's take a moment and switch into Desmos. So Desmos is an awesome tool to see what's happening here dynamically and visually. No, you won't be able to use Desmos on your test. I can hear people asking it right now. But it is a good tool to illustrate. So here I've graphed exactly what I graphed on paper. I did my f of g of x in blue. I did g of f of x in red. And the g of x function, you didn't have to graph that, but I have it here for reference in purple. You certainly could have graphed f of x. I don't think it helps to illustrate much, but you'll notice that it's just 2x, but it's this transformation by a factor of 2 that we're interested in. So I'm going to turn that off for now. What I wanted to point out was when we take the g of x function and multiply the outputs by 2, we get this beautiful y-axis transformation. You can see that dilating as it goes from 1 into 2. So just g of x would be when a equals 1, but then you can see it here dilating into 2 as it transforms itself into that f of g of x composition. So that's all of the y values stretching further away from the x-axis. You can see that happening there really nicely. And then, you know what we could do? We could make it only go one way. There it goes. Now it only dilates. Aha, never goes back. It only stretches further away from the y-axis. We'll have to do that with this one better too. Okay, so I'm going to turn this off now. Put it back. And now, if we think about what's happening as the purple graph goes to the red graph, g of f of x, the dilation of the x-coordinates toward the y-axis. I'm going to turn on this one. And you can see this is only the x-coordinates stretching inwards. The y-coordinates aren't changed at all. The x-coordinates, as this value goes towards 2, you notice the value is getting bigger, and the x-coordinates are getting stretched inwards. They're compressing towards the y-axis. So that's just an illustration of what we already know to be true, which I think is helpful for visualizing the process. Anyway, hope that was helpful. And now for the third problem.